suppose que you remember 3-dimension coordinate is like that. It's a corner using your imagination in 3-dimension. This is the x-axis, this is the y-axis, this is the z-axis. And we have the univector, the orthonormal univector. Univector, remember, the magnitude is 1. The famous orthonormal is called I. Okay, this is any vector you can write like that. And the normal, the univector is this, like a hat. I hat, J hat, and K hat. And by the way, I hat is the vector 1, 0, 0. J hat is the vector 0, 1, 0. And K vector is 0, 0, 1. So we have 1 is the unit vector because the magnitude is 1. But in the Z direction is K, and the X direction is I, and the Y direction is J. Clear?
Yes.
You know that. Okay, now let's practice now in the plane. In the plane again. You have a point, for example, you have a point P1, 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 P1. P1 is the point, no vector, no vector so far. Is -1, 2, 3. And P2 is the vector 4, 6, 2. And you plot the point. How you plot the point? It's not easy to see in the whiteboard. However, I create the GeoGebra to see that, but that's not important. You see after. The most important for me now is, for example, using distance formula. Distance formula. So distance between P1, P2 segment. So we have 2 points in 3D. Okay, promise you see now in GeoGebra when they switch in the screen to GeoGebra. And my goal is connecting P1 and P2 in the space. P1 and P2, and we have a segment, and you find that distance, the length of this segment. And the formula is very, very similar in 2D. Okay, we studied in Scalar algebra, but now in trigonometry, we extended the idea for 3-dimension. Entonces, square root x2 minus x1 squared plus y2 minus y1 squared plus c2 minus c1 squared. And everything enclosed in the square root. Our specific example is, okay, this is x1, y1, c1 example. Doesn't matter what you call 1 and 2, the answer doesn't change. Because the only change is the sign, but when you square, everyone convert to positive. This is x2, x, y1, y2, sorry, and c2. Now, it's big square root. Now you're subtracting. For example, x2 is 4. And x1 is -1, entonces plus, no? You have the minus, another minus of the formula become positive. Okay, y2 is 6 minus something, y1 is 2. Okay, no, it stays the same because it's positive. Square plus c2 is 2 minus c1 is 3 square. Okay, super. Entonces this is 5 squared, que 25. This is 6 minus 2 is 4, square 16. And 2 minus 3 is -1, and -1 is square 1. No? So actually it's 25 plus 16 is 41, plus 1 is 42. Actually it's square root 42. And the square root 42 is in decimal approximation, I put in the calculator, of course, is 6.48. Okay. Everyone follow me this idea?
Yes.
Aha. However, I want to explain another idea before go to GeoGebra to see geometrical in 3D elegant, que es the position vector. Que this concept is similar in 2D or in 3D. Position vector. So basically, we have the famous point. Suppose I want to find the position vector P1, P2. P1, P2, like that. Well, the position vector, the amplitude is exactly the same of the distance, but the direction depends, no? Is in between P1, P2. So the order is important. P1, P2, that means que P2 is the arrow and P1 is the tail of the vector. Okay, position vector. The amplitude is the same. It's radical 42. However, the magnitude, the formula is the same. So magnitude P1, P2 vector, position vector que connecting 2 points on the space or on the plane, doesn't matter, is the square root 42 or in decimal approximation 6.48. No problem. However, I want to spread like a vector. Entonces you have 3 components, X component, Y component, and Z component. To find that, you are doing exactly the same. Look, similar to this, but no square, no square. So in the first box, we have the point. Okay, the point is 4, 4, 4, minus, okay, the formula is x2 minus x1. Likewise, is y2 minus y1 and z2 minus c1. In this case, because I suppose that the arrow of the vector is p2. See, the arrow of the vector is in the opposite direction. Well, entonces you're subtracting x1 minus x2. In other words, we get the same number, but opposite sign. That means that our vector pointing in opposite direction. But okay, let's do it one way. Look, x2 is 4. Minus plus 1 is 5. Comma. This is 5. Comma. Y2 is 6. Minus 2 is 4. Comma, the last component, Z component is 2 minus 3, que es negative 1. So my vector is position vector 5, 4, negative 1. The student can prefer express it, his vector, not in that notation, some students prefer using like a function of the unit vector in any dimension. This is 5i plus 4j minus k. Because the coefficient is negative 1, and negative 1, it's invisible. You put negative 1 here, it's okay, but no, I don't like. Do you understand the idea about the position vector? Suppose the position vector now is P2, P1. Oh, it's the same magnitude. It's the same magnitude. However, the direction is opposite. So it's negative 5, negative 4, and positive 1. It's negative 5i minus 4j plus k. This idea is clear. Position vector and distance. Clear or confusing? Clear or confusing? Clear or confusing? It's
But
clear.
Professor, I'm just wondering that why do we use the K?
K is when it's 3 dimension. If it's 2 dimension, we have only I and J. We have the plane. But I want to discuss in this subject not only vector in 2 dimensions, only vector in 3 dimensions. Therefore, we include K. K is the unit vector coincident with the direction of the z-axis. Make sense?
It does. Thank you so much. So we can do it like in both ways, right, Professor? The
Yeah.
first way to do it and the
Entonces,
second way.
the operation that we study after this, we are doing 2 dimension, 3 dimension, 2 dimension, 3 dimension. And 3 dimension, we include K. And 2 dimension, no, I and J only, right?
Right. Thank you so much.
Okay. Let's move into the...
Sorry, Professor, can I? Oh, I don't think you can come back because I wanted to take a picture, but it's okay.
Take a picture, take a picture.
Oh, okay.
Do you see whiteboard or no?
Yes, I can see it. Okay,
Okay.
in a second. Okay, I already took it. Thank you, Professor.
So in this moment, you don't see the whiteboard, no? Oh, yes.
No, I just see a black square.
Black. So that means it's important for me to understand because I don't see your platform. So now I need to share. Switching to here. Do you see?
Yes.
Okay, Noela, look, I'm the students. This is the... What's going on? What's going on?
Someone is talking.
See. Now let me see. Okay, busy?
Yeah, she already on mute.
Yeah, I put it mute. Okay. I don't know why the GeoGebra is now frozen a little bit. I suppose K need to do something. Oh, waiting. Okay. I frozen. Sometimes happen, no? You and my laptop I open, but in my computer is frozen. No, don't worry. I
Try to
close.
refresh the page, Professor.
No.
No?
It's an idea. Okay, there you go. Now I open again. Open again. Okay. I open again. Is this distance and position vector. Do you see that?
No.
No. Again, I need to share. Okay. Now you see, right?
Yes.
Beautiful. Okay, this is the example, exactly the same, the example that we are doing in the whiteboard. Do you see now here in GeoGebra? And for example, I plot the point, well, actually it's 2 points, no? I call PQ, no P1, P2. I call, when I did this script, I call PQ. But okay, let's focus on P. And Q, sorry. Q. Okay, it's important to explain something. Look, we have 3 axes. The red color is the X. This is a convention in GeoGebra. The green is the Y and the blue is the Z. Clear?
Yeah.
Entonces I put available that point Q. Do you see the point Q? Let me rotate to see more clear. Ooh. In 3D. To understand much better, I create some segment, for example. The first component is 4. Is 4. No. It's 4. AD. It's no. Yeah. It's 4. The second component is 6, and the third component is 2. Do you see? Let me rotate to see. Wow, look at that. This is the 2D picture in which you don't see clear the z-axis. So the component x is 4, the component y is 6, and the component z is 2. Que es the height. Clear now? Wow. Do you understand how you are doing any point?
Yes.
Okay.
Professor, can we do it on Desmos?
No, Desmos impossible to do in 3D. Desmos is not created for 3D. And GeoGebra, yes. 2D and 3D. Pero Desmos is easier. Pero okay, this is very, very intuitive idea. You open, or if you want, I send to you the script and you try to open your computer, no? It's the same. Okay, this is the idea of the position. Okay, next idea. Everyone follow me so far? Everyone
Yes.
follow? Aha. Now I plot the second point. Boom. Okay, P. PQ. And the whiteboard I call P1, P2. But this is the same, right? Aha, I try to do a segment connecting P1, P2. Let me show you. Boom, it's a segment. Do you see the segment? And the length of this segment I found was 6.48 something, no? Look at that here, 6.40, segment PQ. GeoGebra compute automatically you create a segment and compute the length, the magnitude. No magnitude, distance between PQ. Okay, super. Let me delete that. Now position vector. Position vector, do you remember? Okay, was 5, 4, -1, right? It's a vector like that. Boom. No, this vector. Boom. And this vector, when you type in GeoGebra that component 5, 4, -1, GeoGebra suppose que the tail of the vector is 0,0,0 is the origin. And this actually is no position vector. But the position vector is the vector que connecting both vectors. Look, boom. Do you see? Do you see? Okay, and the only thing I want to show you around. A little bit understandable 3-dimension problem.
Yeah, but algebra part, it's easier.
Yeah, absolutely. Absolutely. The most important is the interpretation of this. And don't worry because we're working 2-dimension, 3-dimension. I skip 2-dimension, I jump 2-dimension, 3-dimension. And you study different thing in both dimensions. Okay. Now let's move on to the whiteboard again. Okay. Okay, whiteboard now. Okay, do you see whiteboard?
Yes.
Okay, let's practice a little bit operation with the vector in 3 dimensions. Suppose examples. Suppose that you have vector B, que es the vector 2, 3, -2. And we have another vector W, que es the vector 3, 4, -4, 5. And you add in the vector, why not? It says B plus W. Let's do the operation. Let's do in this operation B minus W. And we have another operation that is 2B minus 3W. Okay. And the first operation we have the easy addition vector. This is super easy. You add component by a component. 2 plus 3, 5. 3 minus 4 is negative 1. And minus 2 and positive 5 is positive 3. Clear, right?
Yes.
And subtraction is similar, except that you change the sign. Suppose you mentally do W negative is negative 3, positive 4, and negative 5. And you adding B, the original B, and minus W. Oh, mentally, you subtracting, and that's it. So is when you're subtracting is 2 minus 3 is negative 1. Comma. 3 minus 4 is positive 4, entonces 7. Comma. Negative 2 minus 5 is 7. Negative 7, sorry. Do you see or no? Doble minus es positive. Good or not good? Follow me or no? Do you
Yes,
understand?
Professor, it was good. Yeah.
Okay, now the third operation is multiplication. Vector B times scalar. Que 2 is considered scalar, and scalar is just a number. And the only function, or the only work of this number is multiplication by 2, the vector. So now my new vector is parallel to the vector B, but the magnitude is twice or 3 times, doesn't matter. So for example, 2B is multiplication by 2, the vector B. Entonces es 4, 6, and negative 4. Do you understand this? This is 2B.
No, we multiply like the 2 by 2 and 3 and negative 2, right? Okay,
By negative 3. Entonces es minus 3W es multiplication by negative 3W. Entonces es, or you write minus outside, either way, multiply by another possibility of the interpretation is, this is subtraction, and you multiply by 3, no? By 3 W. Entonces 9 minus 12 and 15. Makes sense? So the only thing I did was multiplication by 2, any component of the vector B, and multiplication by 3, any component of the vector W. And finally, subtraction. Subtraction is 4 minus 9 is negative 5, is 6 minus 12 is 18, comma, negative 4 minus 15 is negative 19. That's it. Let's practice. Everyone follow me? It's easy, eh?
Yeah.
Now, suppose another operation, number 4 operation. Suppose magnitude of the vector B, by curiosity. Compute that. Magnitude, remember, the formula is square root, any component is square. And the component for the B was 2, 3, and negative 2. Entonces es 2 square plus 3 square plus negative 2 square. Be careful with the sign. Entonces, square root 4 plus 9 plus 4 es 17. Leave it like that, or no? Put in decimal percentage. Suppose another vector to finish the operation. Suppose another vector I call maybe U. The U vector is a vector 2, negative 3, negative 6. Yeah, I want to find the unit vector. Unit vector of U. Unit vector is a vector que travel in the same direction of U. Suppose que U is this. And the unit vector is a vector in the same direction, but But let me call, well, univector. Univector of U es one vector que travel in the same direction, so it's parallel or coincident with the U vector, but the length or the amplitude is 1. That is a reason it's called univector. And it's very, very useful because indicate direction. So you want to indicate direction, not necessarily, and what direction? And the direction of this univector, boom. And that's it. To find the univector, the first thing you should do is find the magnitude of U. The original vector gets given. Okay, it's square root 2 squared plus -3 squared plus -6 squared. Okay, entonces 4 plus 9 plus 36. Oh, es 36 plus 13 es 49. And the square root of 49 is 7. This is the magnitude. So this vector is in one specific direction, but the magnitude is 7. So that distance is 7. However, I need the unit vector in the same direction. Entonces, super easy. The unit vector in the same direction, unit vector in the same direction is, you take the U vector, que es 2, -3, and -6, and you divide it by 7. The fact que you divide it by 7 means que the magnitude of this vector is 1. So the magnitude of the unit vector is 1. Make sense or no?
It does.
Okay. Okay. This is the idea, the basic idea in 3D. I promise that we come back again to the 3D to see more clear idea, no? Pero, okay, so you understand everything, let's move on to the another topic, super important. It is the dot product. Okay, important. Dot product. Dot product. Okay, dot product is one special way to multiplication vector. Dot product. Entonces, what is definition? Definition. And what after you see application? Definition of dot product. In 2D, suppose we have two vectors. The vector A, and you indicate like that, dot product. You know, A is a little bit dot, but it's dot ball. So you put like that as multiplication, as the regular multiplication. Or not necessarily nothing. You multiply a scalar times a number, not necessarily put dot. But in this case, important dot is ball dot. That indicate dot product. And suppose that vector A and 2D have this dimension, A1, A2. And B, dot product, B1, B2. And the formula to compute the dot product is to multiply component by component, A1 times B1 plus A2 times B2. Unbelievable, but it's true. This is a vector. Okay, this is also vector. And the answer for the dot product is scalar. It's just a number. Entonces I want, don't worry for this. This is just definition. Nice to meet you. You understand now. However, what is the interpretation of this scalar? This is the idea in 2 dimensions. The idea in 3 dimensions is very, very similar. But in 3 dimensions, suppose we have 2 vectors again, but the component in the vector in 3D is 3 components. A1, A2, A3, dot product, B1, B2, B3, and the formula for the dot product is exactly the same. It's A1B1 plus A2B2 plus A3B3. Super.
Yes.
This is definition. However, we have another formula for the dot product. Entonces, what formula are you using, Professor? Definition or other formula? No, you're using both to see application. Another formula is dot product magnitude. Another formula, magnitude of the dot product is equal magnitude of the vector A, que es the first, multiplication magnitude vector B cosine theta. And who is theta? Well, theta is the angle in between the vectors. Suppose that you have vector A, you have the vector B, and this is theta. It's the angle in between both vectors. And this is a fantastic application. So one application is you want to determine the angle in between two vectors, you apply that formula. You compute the dot product in between two vectors and divide it by magnitude of the first vector times magnitude of the second vector. And this is cosine theta, and theta is then cosine inverse of the magnitude dot product divided by magnitude of each vector separately. And it's a fantastic formula. And this formula is valid in 2D and 3D. Let's see some example in 2D and switching to the 3D. Pero slow down because it's a little bit complicated to understand this. Do you follow me so far? This is the theoretical part, right? You know, theoretical. Theoretical. Is what?
I asked if I can take a picture.
Yeah. No problem. Definition.
Thank you, Professor.
Let's do an example in 2 dimensions. We focus 100% in 2D. And when you understand very well 2D, we're switching to the 3D. Suppose example 1 in 2 dimensions. Suppose you have a vector 8, que es the vector 2,4, and we have the vector B, que es the vector 4,2. Okay. And what is the question? The question is determine the angle between two vectors. This is the first application. 2 vectors. After we study another application. When you need to find the angle in between two vectors, you using the dot product. Okay, it's doing. You are doing the multiplication. A dot product B. And remember the formula. The formula is too easy. A1 B1. A2 B2. You multiply 2 times 4 is 8. And 4 times 2 is 8. It's a coincidence. Not always happen, but in this case, it's 16. The dot product is 16. And what means 16? Oh, 16 is a number, right? But I want to generalize after. You have conclusion, but no, not yet. Now, this is a scalar. This is a number, no vector anymore. No vector. No. Vector is 2 components or 3 components. It depends if it's 3D. This is just a number. Now I want to use the formula. The formula says cosine theta is equal to dot product. And in this formula, when I explain this, I put magnitude. Have no sense to talk about magnitude of this because dot product is a scalar. This is just dot product. Okay, my formula is a mistake. My mistake. This is cosine divided by magnitude A times magnitude B. And intentionally, I do not specification period here. No. It's multiplication. That's it. It's just a number. Okay, entonces, let's find the magnitude. Magnitude of A is square root 2 squared plus 4 squared. So it's similar to the distance, but in this case we have only 1 point because we are supposed to get another point is the origin, 0.0. Okay, entonces basically square root 4 plus 16 is 20. It's radical 20. You can simplify it, you can if you want, because 20 is 4 and 5, and square root 20 is square root 4 get 2, is 2 radical 5. But it doesn't matter. Okay, and magnitude B, by coincidence, is the same because the only thing I did intentionally was switching the component. But this doesn't matter, it says addition is 2 radical 5. Entonces now the multiplication, magnitude A times magnitude B, es obvio que es 2 radical 5 times 2 radical 5, que es 20, ¿no? 2 radical 5 times 2 radical 5 is 4 times 5, que es 20. As expected. Expecting, no. In this specific example, it's a coincidence. Now, cosine theta is 16, que es the dot product, divided by 20. Its simplification a little bit is 4/5. Now, theta alone is cosine inverse of the 4 over 5. I put in my calculator, I get 36.87 degrees. And this is the angle in between two vectors. Clear or confusing this idea?
Clear.
It's a formula.
Yeah.
And
We just substitute, right?
Yeah. And the questions say determine the angle. No? I want to show you more clear. In two dimension. Look, let me try to find the script in GeoGebra I have in that moment in my laptop. Okay, but I try to find, let me see. Okay, let me try to find. Open. Cross product, 2 dimension. Okay, I have that. Okay, now try to share the screen to this. Switching to cross product. No. Mistake. No cross product. Ese angle in between the vectors. This is I try to find, guys. Projection, no, angle. Oh yeah, I got it. Boom, perfect. Now let me try to share the screen. Yeah. Okay, there you go. Do you see that?
Yes.
Okay. Look, the only thing I type in here is the vector to say how no que GeoGebra understand que it's a vector or it's a point. So you put capital letter, it's a point. So you put lowercase like A, B, C, it's a vector. So the vector 2,4, I plot that. But you see, nice. Que of course it's a vector, position vector que connect the origin and the point 2,4, que this. Suppose, let me try to point the point. Can you see the differences? You put capital A and you open the parenthesis, exactly the same as 2,4. 2,4. Press enter, bang. What's going on? Point. I have a point here. 2,4. Look, it's already done. 2,4. Do you see the difference? So you put capital letter, it's a point. So you put lowercase, it's a vector.
Yes.
Okay, it's amazing. Open, it's free, guy. You open and you practice. And the video is recording, you watching the video again. You put a value. Look at that. This is a point. Actually, capital A is a point in blue color. And little a is 2,4. The same component, but it's a vector. And the B vector is this. And you perform a dot product. A dot product is super easy. Look, in this line, I did the A times B. Now your specification, A times B. Entonces, GeoGebra suppose que si A is a vector, multiplication by B, que es another vector, is a dot product. I multiply and give me the scalar. And the answer was 16. Nice. And the angle in between A and B is that angle. Boom. Look at that. Same answer. Okay, computed by hand and the whiteboard. Do you see?
Yes.
So let's practice more example of the dot problem in 2 dimensions, and you little by little understand the importance of the dot problem, at least one importance. Okay, I go to the whiteboard again. Okay. Okay. You see whiteboard?
Yes.
Example 2. Again, the same application of the dot product. Example 2. Well, we have this vector, A vector. Okay, by the way, I copy exactly the same A vector, 2,4. Repetition again, A vector is the same. But now, C vector, another vector. Okay, it's the vector -4,1. Okay, and the same job. Determine the angle in between this vector. Okay, no problem, I understand. You are doing the dot product. C, sorry, no B. Okay, multiplication. Multiplication is -8. Oh, no vector anymore. No, it's a scalar. It's -8. So 2 positive times -4 is -8. 4 times 1 is 4. And the answer is -4. Ooh. In this example, the dot product is negative. What would be the interpretation when the dot product is negative? In this example 1, the dot product was 16, it's positive. However, in this case, it's -4. So I need to discover what is the interpretation when the dot product is negative. No idea. Okay, now if you wanted to find the same formula, cosine theta, remember it's the dot product of this vector divided by magnitude of A and magnitude of C, and multiplication each other. Entonces es -4, es the dot product, pero the magnitude never is negative, it's positive, ¿no? Entonces magnitude A, I computed before, que es radical 20, ¿no? Radical 20, I did that. I did that. Magnitude C, no, I need to compute. This is square root, -4 squared plus 1 squared. It's 17. Okay. Now multiplication is, you combine if you want. This is 20 times 17 is, let me put in the calculator. 20 times 17 is 340, ¿no? Times 17, yeah, 340. Entonces es -4 divided by square root 340. We can simplification, but no important. You put in the calculator. Actually, I did that. My calculator is 2 radical 85. But it's not important. Now, theta alone is cosine inverse of -4 divided by square root 340. And you expect, when you find cosine inverse of the negative number, that means that the angle is in the second quadrant. Makes sense, right? Do you remember the trigonometric inverse function? And the answer,
We need to put it in calculator, right, Professor?
Yeah. Please put in the calculator. Come on, let me try it in my own calculator. Is you put cosine inverse of -4 divided by square root 340. Close the parenthesis. Entonces en my calculator I need to say I want the answer in degree. In degree the answer. Entonces now angle degree. I try to find the function que convert to degree. Press enter. 102.52 degree. 53, 52, doesn't matter. Do you see or no? You did in your own calculator?
Yes, Professor.
You get
It
the
gave
same
me a
answer?
different result, though. I think mine is not in degree.
A ver. But you have set up your calculator in radians?
Yeah.
Entonces switching to degree?
Okay, I'm doing that.
Come on, do it quickly. This is important, guy. I don't know if for you it's important. You verify because
Yeah,
it's
you're right, Professor. Now it gave me the same result. Yeah.
okay, beautiful. So the conclusion is, look at that. When the dot product is positive, let me find conclusion. Not completely conclusion, but a partial conclusion. When you perform dot product and the dot product is positive, it's because the angle in between the vector is acute, so less than 90 degrees. So one indicator, good indicator, you multiply the vector using dot product. If the answer is 40, 16, 20, positive, I guarantee you 100% that the angle is acute, less than 90 degrees. However, when you multiply and the answer is negative, you obtain obtuse. Angle que es in between 90 and 180, no? So theta lie in between 90 degree and 180 degree. One good indicator. Let's see what happened in the next example. It's very, very interesting. Very, very interesting. Example 3, dot product in 2 dimension, guys. Example 3, dot product in 2 dimension. Suppose that I need to find the same thing, but in 2 different vector, different name. B vector is a vector 3, -1, semicolon, and W vector is 6, -2. Okay, let's do it. Same procedure. You perform dot product, B vector, dot product, W vector. Okay, this is 18, 3 times 6, 18. And -1 and -2 together is +2 is 20. It's 20. It's 2, sorry, it's 2. And the answer is 20. 2. Positive 2. And the answer is 20. So that indicates one, okay, is acute, maybe, no? Acute. But let me finish to find theta, the actual theta. Entonces es magnitude of B is square root 3 squared plus 1 squared. Well, actually it's -1 squared, no? Pero negative 1 squared is 1. So the answer is square root 9 plus 1 is 10. Radical 10. And magnitude W, exactly the same. It's a square root 6 squared plus negative 2 squared. It's 36. Plus 4 is 40. Okay, let's do it. The formula of the cosine theta is dot product, in this case B dot product W. Okay, the answer was 20 divided by magnitude of P multiplication magnitude of W. Okay, this is 20. I computed before, and this is radical 10, and this is radical 40. And radical 40 and radical 10 together is radical 400. And square root 400 is 20. And 20 divided by 20 is 1. Wow. It's 1. Okay, now the theta value is cosine inverse of 1. Yeah, I know by memory que what is the angle whose cosine is 1 is 0 degree. Es 0 degree. Entonces now one, this is no fantastic discover because you can see that this vector B and W are parallel vector. And what is the super easy way to discover they are parallel vector? Look, if you multiply the vector B by 2, you get the vector W, right? Because look, 2 times 3 is 6. And 2 times negative 1 is negative 2. Wow. So W is a big vector and B is a half of the vector. And when you multiply by 2, this is parallel vector. One possibility is doing this long process of the dot product and you discover que es 0 degree the angle in between the vector. Pero no. The easy way is you divide component by component in 2D or in 3D. It doesn't matter. You divide 6 divided by 3, 6 divided by 3, and you divide negative 2 divided by negative 1. See, the answer is the same. This is parallel vector. In 3D, we have 3 components. You need to divide the third component, and the answer is the same. Clear? Clear or a little bit confusing? Parallel vectors. Hey, answer me. What's going on? Are you there or no?
Yes.
You are. Do you understand the parallel vectors?
No, sorry, Professor. I was in the restroom. I got back now.
It's okay. It's okay. And the rest of the students, not only Nuela. It's okay, guys? Parallel vector is okay?
Yeah.
Yes, Professor.
Okay, Nuela. Entonces now we determine the angle. And suddenly happen that the angle is 0 degree. Si es 0 degree is because this is parallel. Okay? And one way to checking si it's parallel, you divide component by component. You divide, for example, 6 divided by 3 is 2. And negative 2 divided by negative 1 is 2 also, right? And the answer is always 2. Well, not necessarily 2. A number, a constant number, that means that the vectors are parallel. Make sense?
Yes, it does. Thank you.
At the beginning, I don't know. I tried to prove it by the traditional method. This is the formula, that formula. Look. Okay. Now, one more example in 2D. This is the last one. Yeah, I propose to go to the 3D after that. Example 4. All right, let me make it zoom. Example 4 in 2D. Well, it's a vector B again. Okay, it's the vector 2, comma, negative 1. And we have a vector W. que es another W, is 3,6. Okay. Now, I need to find the angle in between this vector using the idea for the dot product. Multiplication. Is 2 times 3 is 6, and negative 1 times positive 6 is negative 6, and the answer is 0. Wow, it's 0, the dot product. What means? Que the dot product is equal to 0. Well, according to the formula, look, cosine theta is equal to B dot product W divided by magnitude B multiplication magnitude W. See, this answer is 0 is because the numerator is 0. I don't care the denominator. The denominator is not important. Entonces, cosine theta equals 0 means que theta is 90 degrees. O sea, these vectors are perpendicular. Professor Anthony Esposito here. I am the doctor. Okay. Advantage and disadvantage of the online class. You can go to the doctor one time and you switch into the lecture. Okay. The important information is this is perpendicular. So you are doing, for example, the vector B and the vector W. I suppose is, I don't know. Okay, no, vector B. Let me try to use my imagination more clear. The vector, suppose these vectors. The vector B is 2, negative 1. 1, 2, negative 1. This is the vector B. The component in X is 2, and the component in Y is negative 1. And the vector W is 3 and 6. 1, 2, 3, 4, 5, and 6. Wow, amazing. This vector is 3,6. And this angle I discovered mathematically is 90 degrees. Okay, conclusion. Application dot product. Or at least first application dot product. When the multiplication to vector A times dot product B is a positive number, that means that the angle is acute. When A dot product B is a negative number, is obtuse, the angle, greater than 90 degrees. And when the dot product, the answer is 0, that means that the vectors are perpendicular. And the terminology they're using in the book, in the other lecture, is called orthogonal. Orthogonal means perpendicular. So some books say, prove that these vectors are orthogonal. Okay, you perform the dot product, the answer is 0. Yes, they are orthogonal or perpendicular, get the same. And parallel, a little bit the dot product fail, because you get the number acute, obtuse, but you have no idea si es. So the traditional way to prove that two vectors are parallel is, suppose that we have 3 vectors, A, B, C. And this vector is 1, 2, 3. No, 2 dimension. 1, 2. And this vector is 2, 4. And this vector is 2, 6. And you want to prove mathematically that A vector and B vector are parallel. Easy. You take component by component. You divide 1 divided by 2. 1 divided by 2. This 1 and this 2. should be equal, I claim that, 2 divided by 4. 2 divided by 4. Oh, it's okay. So A vector and B vector are parallel. And what about C? Well, I have no idea. You divide 1 divided by 2. 1 divided by 2. Should be equal 2 divided by 6. Oh, no, it's completely wrong. This is 1/2 and this is 1/3. It's completely false statement. Therefore, B, A, and C, no parallel. Do you understand this? The proof of the acute, the proof of the obtuse, and the proof of the orthogonal or perpendicular, and the proof of parallel.
Yes.
Yeah, okay.
So, Professor, the 3D is the same process?
Say again?
With the 3D is the same process?
Yes. But you always anticipate my word. Now, let's see at least one example of the 3D now. Okay, it's the same process. Nola, yes, you're right. It's the same process. Let me 3D now. So the time is not too much to say I want to do one example of the 3D. Suppose 3D dot product. Let me set out the problem. Okay, suppose we have the rectangular coordinate system in 3D. X, Y, and Z. I promise I can show you this in GeoGebra, but I try. And we have different points. Suppose okay, we have the point P, no vector, point P, que es the point 1,0,1,0,0. I plot that 1,0,0 lie on the x-axis. And the point Q is the point 0,1,0. Okay, using another color here. Is a point, this is a point Q. Is 0,1,0. And this is a point P. And we have the third point to complicate your life. R, que es the point 0,0,2. Okay, entonces here. Let me using another color. Green maybe. 1, 2, here. Is a point R. Is a point 0,0,2. So far, everyone follow me?
Yes.
Okay. Now, I want to find the vector PQ. Position vector. Well, position vector PQ is the vector in that direction. It's a vector que connecting P and Q. And I suppose according to this terminology or notation, Q is the arrow, look, Q is the arrow and P is the tail. Make sense?
Yes.
Aha. We have another vector. It's a vector PR. It's a vector que connecting P to R. Like that. And this is another position vector que connecting the point P and the point R, pero R is the tail, is the arrow, sorry, and P is the tail. Make sense? My goal is find the angle. Data in 3 dimensions. This is my goal. Well, the only tool that I have in my hand to find, you can use a geometry, but it's complicated, very complicated. However, so you find this vector, PQ and PR, and you perform a dot product, and you apply the formula for the cosine theta in 3D, you can do that. So the vector PQ, is the vector, look, you subtracting Q minus R, because remember this is X2, XY2, and Z2, and this is X1, y1 and c1. Entonces you're subtracting 0 minus 1 is -1. That component -1. Comma, 1 minus 0 is 1 positive. Comma, 0 minus 0 is 0. Do you see that position vector?
Yes.
Aha. PQ, 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 PQ. Now another position vector is PR. Is subtracting, pero subtracting who? R minus P is -1 again, comma 0, comma 2. Okay, 2 minus 0, 0 minus 0, 0 minus 1 is -1. It's nice. And now, why not you perform a dot product? PQ dot product. By the way, I forgot to say some important property. So you are doing in this order, the answer is exactly the same as you are doing in this order. So the dot product is completely commutative. Another product we studied, not today, of course, is not commutative. The ordering is important. And the dot product is nice. The ordering is not important. So you multiply. You multiply. Multiply who? Multiply component by component. This times this is 1, pero no vector. Hello, it's a scalar. So -1 times -1 is 1. Plus something, 1 times 0 is 0, and 0 times 2 is 0. The answer is 1. The dot product is 1. And that means that this angle is acute, no? At least it's acute. Okay, let's continue with the formula. You determine the magnitude of PQ vector, que es square root -1 square plus 1 square plus 0 square. Es obvio que es radical 2. Because -1 square is 1, 1 plus 1 is 2, 0 is nothing, es radical 2. Now magnitude PR is square root that -1 square again plus 0 square plus 2 square. Entonces 1 square root 1 plus 0 is nothing plus 4 es radical 5. Es radical 5. Okay. Okay. Do you follow me? Everyone follow me?
Yes.
Now I go to my famous formula. Cosine theta is equal to the dot product PR dot PQ we did before. The answer of this is 1 divided by radical 2. Bueno, que es magnitud, sorry. Magnitude PR multiplication by magnitude PQ. Es radical 2, and radical 5 es radical 10, ¿no? So cosine theta is 1 over radical 10. Okay, and now find cosine inverse. Cosine inverse of this. Okay, we expect logical, okay, it's acute value, acute number is 71.5 degrees. Okay, try to check it in your own calculator.
It's correct.
It's correct. Okay, super. Now,
it's acute.
say again.
Is it acute?
It's acute. Of course, it's acute. Because acute is less than 90 degrees. Okay? This is definition acute. Acute is an angle less than 90 degrees. Obtuse is greater than 90 degrees. Oh, no, in between 90 and 180. Second quarter. This is the first quarter, obviously. Okay, I don't know if I can find or no. In GeoGebra, I have some script for that part. Let me try to open. A ver, in 3D. Distant 3D. Distant position. No, let me try to find another folder. This is the distant position. Angle in between the vector. Okay, I suppose it's this guy. Okay, I got it. Look. Let me share with you the screen. Boom. boom, 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 and boom. Look, do you see or no?
Yes.
Okay, look. Let me try. You can set the grid to see more clear if you want. It's totally optional. And you have the famous point PQR. Look at that, PQR. P, Q, and R. And put the vectors. And the angle is, look at that. Look at the answer. 71.56 degree. 57 degree. Super, super. We are the best. Okay, next time we study another application for the dot product, and we study also another operation with the vectors. Amazing. Okay, this is useful in physics, guys. Okay, do you see my face now?
Yes, Professor.
Okay, have a nice day. I am leaving.
You too. Bye-bye.
Bye-bye.
Okay, Professor.
No, Professor, before you go, Courtney has a question. Did you
Go ahead.
read?
Well, any person email me, no?
No, Professor, it's just like about the test because it says on syllable that it's on 24th. So
No. I change. Don't worry, your mom I specific. You continue working in the homework, right?
Okay.
Okay.